Hey everybody, hope you guys are having a fantastic day. Thanks for tuning into this video. In our last video, we worked on solving rational equations. There was an equal sign, we were trying to find the solutions. X equals what, or X equals what, that type of thing. Well, today we're going to mostly get rid of that equal sign and work on simplifying when we are multiplying or dividing rational expressions. Okay, so rational expressions, expressions aren't equalities, there's no equal sign, all right? But before we do that, let's do a quick review of domain, because domain is going to show up quite a bit here for us, all right? So I'm going to put an equal sign here and say y equals 3x plus 1. Now, I hope that when you take a look at this, okay, y equals 3x plus 1, you can quickly spot that x can't equal -1. We talked about domain quite a bit at the beginning of the year. We cannot have a 0 in the denominator. Okay. So our domain for this first one is x is an element of -infinity to -1 exclusive union -1 to infinity, everything but -1. Okay. Now, when we look at our second one, okay, we say, okay, where's that denominator equal to 0? Well, let's factor this. Okay. Our denominator factors here to x plus 3, x minus 3, doesn't it? Okay. So our domain on this one would be everything but plus or minus 3. So -infinity to -3, union -3 to 3, union 3 to infinity. So everything but -3 and 3. But you know what? Since we are factoring the denominator, let's factor the numerator while we're at it. That factors to be x minus 7, x plus 3. Now, what do you notice here? Well, I notice there's an x plus 3 in the numerator and denominator, and they're products in the numerator, product in the denominator, so these cancel. So this would actually simplify to be y equals x minus 7 over x minus 3. But notice if I do that simplifying first and then look at the domain, I would only say x can't equal 3. However, when I look back at the original, I know x can't equal 3 or -3. So it's important when you can think about domain to think about what the original function is and what can't go into that. All right? Okay. Now let's take a look at the graph just to confirm this. If I were to graph just x minus 7 times over x minus 3, it looks like this. And we see very clearly that x equals 3 is not in the domain. If I type in x equals 3, that's the vertical asymptote right there. All right? But what if I were to graph the original? Are they equal, right? Is our original equal to just x minus 7, x minus 3? Well, when I graph them, they are the same, right? Are they the same everywhere? It looks like it, but we got to be careful here about something. Notice, x equals -3, okay, is in x minus 7, x minus 3. But when I graph the original, okay, we see 3 is still a vertical asymptote, but now when I go to -3, what is there? There's a hole in the graph. Because we know when we look at this function, x can't equal -3. We end up with a 0 in the denominator. Okay, so we end up with -3 not being in the domain. All right, so what we're going to do today is if we are simplifying, which we are going to be doing, okay, and we take something like this and we simplify it to this, it's important that we make a note here. It should be obvious to us that 3 is not in the domain, so we don't need to make that note, but we do need to make the note that x can't equal -3, okay, because of what's in the original. Okay? Because if I were just to make this statement, if I were to say x squared minus 4x minus 21 over x squared minus 9 equals x minus 7 over x minus 3. Is that true? Are these really equal? No. They're equal everywhere but one point. Where's the point where they're not equal? When x is -3. So as we simplify today and we say something's equal to something else, Well, if there's a factor that was in the denominator that got canceled out, we have to make the note that this equality is not true for when x equals -3. Because in this one, when it's -3, it's undefined, where this one, it actually has a value, right? It would be what? -10 over -6. All right? So I'll keep looking at that at each example and explain that. So let's start with just another simplifying problem. Okay. The first thing we want to do is we want to factor this. Okay. Factor the numerator, factor the denominator. Well, when I look at the numerator, I can factor out a 3x squared. And that leaves me with 2x minus 5. In the denominator, I can factor out a 6x, and that leaves me with 2x minus 5. Okay. Now notice what happens here. The 2x minus 5's cancel. And when we have an x squared over an x, this x cancels out one of those, and then the 3 and the 6 reduce to a 1 and a 2. So what's left in my numerator? 1x. What's left in the denominator? Only 2. Okay. So does 6x cubed minus 15x squared over 12x squared minus 30x equal x over 2? It does. Well, everywhere except for a few points. Because what is not in the domain of the original function? Well, when I looked at the factored denominator, I know x can't equal 0. Okay, but if I look at x over 2, I wouldn't know that, right? So we have to say x can't equal 0. There's also another value that x can't equal. 2x minus 5, add 5, divide by 2. X cannot equal 5 over 2. Okay, this is simplified. This equals x over 2, except for x equals 0 and x equals 5 over 2. And I want to show you with the graph there one more time here. All right, what was the numerator? 6x cubed minus 15x squared. And our denominator was 12x squared minus 30x. Look at that. What's that look like? It's just a line, isn't it? And we simplified it to be x over 2. Notice they're the same, except at a couple points. Okay, what points did we say they're not the same? At 0. Notice there's a hole there. And at 5 over 2, which is 2.5. Oop, there it is right there. There's the hole at 2.5, 2.5. Whereas in x over 2, does that have a hole at 0? No, it doesn't. Does it have a hole at 5 over 2? No, it doesn't. Okay? So as we simplify and we say this equals that, we have to make a note of the excluded values. It's not equal to this because of x equals 0 and x equals 5 over 2. All right, let's try another one. Hopefully we're going to get the hang of this soon. Factor. Four would give me a 12. And a 2 there. 12 is, if that's a minus and this is plus, that's plus 12x minus 2x is 10x. Over, factoring down here. Well, they both have to be minuses, right? And I did a 4 and a 2. Minus 12x minus 2x is negative 14x. All right. So when we look at this and we're simplifying, we say we have 3x minus 2's on the top and the bottom. They cancel, leaving me with x plus 4 over x minus 4. So does this original equal x plus 4 over x minus 4? Yes, everywhere, but what value? What value did we, what factor did we cancel out here? 2/3. Okay, I don't need you to write x can't equal 4. We know that by looking at the simplified version that 4 is not in the domain. I just need to give that excluded value that we don't see anymore. This equals that except for at x equals 2/3. All right? Good. Now, by the way, just want to remind, to cancel things out, you have to have products. I know sometimes students look at this and say, hey, don't those 3x squareds cancel? No, with those pluses and minuses there, with a sum, hey, you cannot cancel. They have to be products to cancel. All right, so let's get to multiplication. Multiplication is really easy, right? If we're multiplying fractions, we just multiply across the top and across the bottom. Numerator times numerator, denominator times denominator. So, just like in the last problems, okay, I'm going to say this is equal to, and I want to factor to see what cancels out. First thing I'm going to do is I'm going to factor a negative out of that. I do not like factoring with a negative first term here. Oh, I got this one right away. That's 2x plus 3, 2x minus 3, difference of perfect squares. This would probably be what? Multiplies to 21. We got to get a 1x. So one of these has to be negative, one has to be positive. If I did a plus 7 here and a minus 3 there, I think I've got it, right? 7x minus 6x is x. Okay, down to this one. I'm thinking 3x and 2x. 28 would be 7 and 4. It's 21 and 8, which is 29x. Both of those are pluses. Excellent. Can we factor this now that I took the negative out? Let's see here. You know what? I might just write that up here. Oh, I took the negative out, but I didn't. Yikes. Good thing I'm rewriting this. Otherwise, I would have goofed that up. Those are both supposed to be minuses. Can't take the negative out of just the first term and leave the others the same. All right, now I took the negative out. Let's see if we can factor this. 3x and a 2x. 8, 2, 6, and a 2. One's a plus, one's a minus. Okay, live on camera, struggling to factor. Here we go. What's it going to be? Three, 4 plus gives me a 9x minus 8x. All right, there we go. Got it. So we factor first. Okay, now we're multiplying, and I could rewrite this in one step, but really, like I said, when we're multiplying, we multiply numerators, we multiply denominators, so it's almost like we can just extend that fraction bar across the two of them, and it's just one big fraction. Usually don't do that, but that's kind of how I'm thinking, because that allows me to do things like this 2x plus 3 in this numerator does cancel with the 2x plus 3 in that denominator, because really it's like one big numerator and one big denominator. So let's keep canceling. 2x plus 7s are gone. Anything else that cancels out? I think that's it. So what are we left with here? In the numerator, negative 3x minus 4 times x minus 3. In the denominator, 3x plus 4, 2x minus 3. All right, so that's simplified. Okay? But we have to make our statement about what can't equal x, or what x can't equal. This does equal that, except for what values? Negative 7 over 2 and negative 3 over 2 from those two factors that we canceled out. There we go. All right, now let's go to division. Okay, not going to be a difficult step for us. Like we said before, the first thing we need to do is to factor. So let's factor out a 2. Let's factor out a 3x. Divided by, let's factor out a 4x. And let's factor out a, what, 9x squared. There we go. Now, don't make the mistake of starting to cancel right now because this is division. Okay? Have to be careful with division. Remember that division is the same as multiplying by the reciprocal. So this is times, let's flip the second, right? Dividing fractions is easy as pie, just flip the second and multiply. So we have 9x squared times 2x minus 5 over 4x times x minus 3. So we change dividing to multiplying by the reciprocal. Now I do like to factor first before I change it to multiplying by the reciprocal. You'll see why in a minute, but let's get our simplifying and our canceling out right now. So now I see these x minus 3's cancel. The 2x minus 5's cancel. All right, what else do we have? Notice in the denominator we have a 3x times 4x. Okay, so we have an x times x, which is an x squared. In the numerator, we also have an x squared. Now I could take the step to write that out, but I know that this x cancels one of those and this one cancels the other one. So there's no more x's. Now what do we have left? We have a 2 and a 4, which reduce to a 1 and a 2. The 9 and the 3 reduce to a 3 and a 1. What's left in my numerator? Only 3. What's left in the denominator? Only 2. So this big, ugly dividing two rational expressions is just the same as 3 over 2. Except now we have to get rid of those values that aren't allowed. Okay? This is not equal to that because in the original, what can't x equal? Well, I know x can't equal 0. In the original, I know x can't equal 5 over 2. I know 0, already have it. 5 over 2, I already have it. But also there's a couple other values that x can't equal because when we flip this fraction on the second one, dividing is the same multiplying by the reciprocal, we also end up with a new denominator where x can't equal 0 and x can't equal 3. We already have 0 on the list, but we also have to get rid of 3. So when you're dividing, look at the original denominators. Okay, I hope you agree that I can't put in 5 over 2 into this because this makes us dividing by an undefined number. But also, I can't put 3 into it either because that means that we are multiplying by an undefined number. So we end up with 3 over 2. All right, couple left. This one, there's no factoring to do. I'm going to just change multiplying to dividing by, or dividing to multiplying by the reciprocal. So I'm going to flip the second. And let's start canceling things out. Take a look here. Notice there's a t squared in the denominator, so there's a t times t. There's a t cubed, t times t times t in the numerator. So 2 of these t's will cancel out 2 of those, leaving just 1. Okay. Notice that there is 1 r in the numerator and 2 in the denominator, so this 1 r cancels out 1 of those, so there's just an r to the first. There's 1 s in the denominator here. That's going to cancel out 1 of those, leaving a s squared. As for numbers, the 6 and the 4 reduce to a 3 and a 2. And I think I've got them all. What do we have left in the numerator? 3 times s squared times 3 times t. So 3 times 3 is 9, s squared t. In the denominator, what's left? 5 times 2, which is 10. T's are gone. Just that 1 r is left. All right, so our original equals this, but there are a couple excluded values. You wouldn't know looking at this that t can't equal 0, and it should be obvious that t can't equal 0. Are there any other values that we can't substitute in? We can't put 0 in this either, can we? Okay, so we also have to get rid of where s equals 0, and there we go. Woo. All right, last one. Hey, oh, back to multiplication. So remember, we don't have to flip the second and change it to multiply. Let's factor y cubed minus 8. Ooh, difference of perfect cubes. Hopefully you're still pretty fresh on difference of perfect cubes. How does that factor? This is y cubed minus 2 cubes. So this is y minus 2, y squared plus a times b, which would be 2y, plus b squared, which would be 4 squared, which is 16, right? So remember, what's our pattern here? A cubed minus b cubed is a minus b times a squared plus ab plus b squared. So you make sure that you're staying fresh. Oops, not 16. That would be 4. There you go, b squared, because this is y cubed minus 2 cubed, so our b is 2. All right, over. Okay. Factor y squared plus y minus 6, that's y plus 3, y minus 2. Times, let's factor the next one. Get this stuff out of the way. Factor out a y. I can factor out a y. Oh, do you see this? What happened? We've been canceling out a lot of monomials and binomials, but notice there's a trinomial here that matches the trinomial there. Those cancel out. Y plus 3's cancel. Y minus 2's cancel. Y and y, those cancel. What's left in the numerator? Well, everything canceled out, so just 1, right? What's left in the denominator? Everything canceled out but 1. So we have 1 over 1, which is 1. So this big multiplication of rational expression simplifies to just 1. However, we would not know, unless we make the notes, that y can't equal what? Negative 3, 2, 0. Is there anywhere where y squared plus 2y plus 4 equals 0? And the answer to that is no. This does not have any places where it's equal to 0. You could use the quadratic formula to confirm on that, but this does not equal 0 anywhere. So this simplifies to 1. There we go. Good. Okay, check my answer again by graphing this. Okay, I'm going to use x's instead of y's so that GeoGebra or Desmos likes this. So x cubed minus 8 over x squared plus x minus 6 times second fraction x squared plus 3x, and the denominator was what? X cubed 2x squared plus 4x. And what do we get? We get that line, right? It equals what? 1. Okay. Now, there should be some excluded values in here. What did we say was excluded? Oh, there's the negative 3 that it can't equal. There's the 0 it can't equal. And there's the 2 that it can't equal. So all looks good. All right, thanks for watching. We'll see you next time.